Alright, this video is going to cover section 1.7, which is inequalities. Several types of inequalities, as you can see listed on your screen. And so it's going to be a little bit longer than the previous one, but I want to be as thorough as possible. Anytime you're working with an inequality, remember that if you multiply or divide by a negative number, you do have to flip the inequality symbol. So if it was less than, it becomes greater than, and vice versa. So this slide just shows us an example of what a linear inequality would be. I know it's linear, just like if I know I have a linear equation as opposed to a different form, because the degree of this equation is 1, meaning the highest exponent is 1 on our variable x. And any of these symbols can be used in an inequality. And so with this one, we're just going to solve this simple linear inequality just as if I was solving an equation, the only difference being that instead of an equal sign, I'm going to have this greater than symbol here. And so I'm going to treat it just as I would an equation by subtracting 5 from each side to start with. So we have negative 3x is greater than negative 12. And then I'm going to divide each side by negative 3. So divide by negative 3, divide by negative 3, I get x. And now the symbol is going to reverse because I've divided by a negative number, and I get x is less than 4. Okay, so that would be the solution of this inequality. And many times you're required to write the solution in interval notation, which we're going to talk about on the next couple slides, and also graph the inequality. But this interval notation would look like this, where I have since x is less than everything, x is every x less than 4, it would be from infinity, negative infinity, to positive 4, like this. And we're going to talk about that in the next two slides, as I said. And the number line that I would graph this on would appear like this. And when I require you to draw number lines, I don't require you to show every number on the number line, just 0, where it would be located, and your number that you're concerned with from your solution, which is 4 in this case. And then this would have like a little parenthesis thing on it and be shaded to the left. Alright, so this one kind of shows you the different types of notations we will be using. This is the one we need to be most familiar with, interval notation, as well as how to graph the inequality. And this notation is used when my symbol has no line underneath, so that number's not included. And that's what the graphs look like for these. And this is the one that we just got finished doing. This one, if I do have a line underneath my symbol, I have to use a closed off bracket, a square bracket, instead of a parentheses. That's the only difference that we need to talk about there. This slide is available in your My Math Lab. This is slide 5 of section 1.7. These notations and graphs are used more with compound inequalities, which we will be getting into in a moment, as well as quadratic inequalities. And the first, the one that is different than the rest really, is this one in the middle, the disjoint interval. And anytime I see the word or in my problem, which we'll talk about, I'm going to have this little U looking notation, and that just stands for the union of. So I want this part of the graph in union with this part of the graph as my solution. And also, if we get a solution that is all real numbers, meaning any number we put in for x would be a solution to our inequality, then that goes from negative infinity to infinity as an interval notation, and the graph would be the entire number line. Okay, so again here I just have a linear inequality. I'm going to treat it just as I would an equation. And so the first thing I need to do is get my x's together and my constants together. So I'm going to be subtracting 2x from each side and subtracting 4 from each side. And that results in the simplified inequality of negative 5x is less than or equal to 3. And then I would just need to divide by negative 5. And since I'm dividing by a negative number, I'm going to flip the inequality symbol and therefore my solution is x is greater than or equal to negative 3/5. And this problem did ask us to give the solution set in interval notation and also graph it. And so the interval notation would be a bracket, negative 3/5 to infinity. And I use the bracket again because of the line underneath my symbol, which means that negative 3/5 must be included. And then when I put this on my number line, I'm also going to put a bracket on that spot, and I'm going to be shading to the right because it's everything greater than that value, including that value. Okay, your book in My Math Lab refers to this as a three-part inequality, but it's also known as a compound inequality because it has more than one inequality symbol. My goal with these types of problems is to keep my variable in the center of the two symbols. And so I want to isolate that variable and get everything else away from it. And I'm going to do that by treating this as kind of a three-sectioned inequality. And I want to first get rid of this 5 by subtracting each part by the 5. And when I do that, I get negative 7 is less than 3x is less than 15. And then I continue by dividing by 3. And because 3 is a positive number, there's no need to flip the inequality symbols. So I'm left with negative 7/3 is less than x is less than 5. And so this would be the solution to this inequality. To write this in interval notation, I'm going to do parentheses, and I have negative 7/3, comma, 5. If I had had a line or equal to part under either one of these symbols, then one of them or both of them would change to brackets. And now I'm going to draw this a number line to represent this solution as well. Okay, and now I'm going to have parentheses on either one of these parts of my number line, and I'm going to shade in between them. And I can remember to shade in between here because x, my variable, is in between here. And so if x is in the middle, I shade in the middle. Next we've got a word problem situation here. It says if the revenue and cost of a certain product are given by R equals 4x and C equals 2x plus 1,000, where x is the number of units produced and sold, at what production level does R at least equal C? So for R to be at least equal to C, I would have to have R be greater than or equal to C. And so what I'm going to do is take 4x and make it greater than or equal to 2x plus 1,000, and then solve this inequality for x. So I've done that here. 4x is greater than or equal to 2x plus 1,000. We subtract the 2x and divide by 2, and since 2 is positive, there's no need to flip the symbol. And so x must be greater than or equal to 500. And so this is referred to as the break-even point. Okay, so this company would have to produce and sell at least 500 of their products in order to break even. So they would want to, of course, sell more than that. All right, next we need to discuss quadratic inequalities, which are going to be similar to quadratic equations, but the inequality part is going to be what's different here. Still going to start off solving them the same way, but how we determine our interval notation is going to be slightly different. So first we're going to need to solve the quadratic equation, just like we would before. We can solve by factoring, we can use the square root property, we can complete the square, or we can use the quadratic formula. And those solutions are not what I'm going to put on my number line necessarily. Those are going to identify the intervals to determine the solutions of the equation. So that's very important. I kind of consider them like boundaries on our number line. And so then between those intervals we're going to use a test value and determine what the solution set is. So here we have an inequality, x squared minus x minus 12 is less than 0. So first of all, I need to solve this quadratic equation just as I would if it was a regular equation. And I'm going to do that by factoring this time because it's easy to factor this particular quadratic. especially since the first term is just 1x squared and not another number other than 1. And so this is going to be, whoops, x and x for the first part of each of my factor. And I need to multiply to negative 12, but add to negative 1. And I can do that with negative 4 and positive 3. And so I would solve each of these for x. X minus 4 equals 0. X plus 3 equals 0. And so I have x equals 4 and x equals negative 3. And so what these become are my kind of boundaries on my number line. So this slide shows you what I mean about boundaries here. The two numbers negative 3 and 4 divide the number line into these three intervals. And so you see here we have the first interval that goes all the way to negative 3. And then we have the second interval, which is the in between negative 3 and 4. And then the last interval, which is 4 to infinity. And I'm going to have to use some test points in each of these intervals to determine which interval is included in my solution. So for instance, I might test the number negative 4 in this section, because it's in this section. I'm going to test 0 in this section. It's always easy to test 0 wherever it is. And then I'm going to test 5 in this last section. And by testing, I mean I'm going to take that value and plug it into the original inequality to see if it satisfies that inequality. And we're going to do that on this next little slide. And so here you see, in the first interval we've tested negative 4 by plugging it into the original inequality here, and I get 8 is less than 0, which is not true. Therefore, that interval is not included in my solution. Okay, then I'm going to test the next interval. 0 was my value for that interval. By substituting in 0 into the inequality, I get negative 12 is less than 0, which is true. And so I know that this is part of my solution to my inequality, interval B. And then the final interval, I test the point 5, and I get 8 is less than 0 here, which is false. And so therefore, the only solution would be the center part of my number line. And it says, here's my solution set here down at the bottom, negative 3 to 4. Notice that I have parentheses because my inequality does not include the line for the equal to part. And if I wanted to graph this on a number line, I would shade the center part of that number line between negative 3 and 4. Okay, here's another inequality that we're going to solve. It's a quadratic inequality. And so the first step would just be to solve it as if it were just an equation so that we can determine our boundary points on our number line. Okay, so this one I'm going to solve again by factoring, but remember if this is not a 1, we're going to have to split the middle term. So I'm going to split this positive 5 into two terms. Those two terms have to multiply to negative 24, but add to positive 5. And those two numbers would be 8 and negative 3. So that middle term, 5x, is going to become positive 8x and negative 3x. And then I'm going to factor by grouping. The first two terms I can factor out a 2x, and I'm left with x plus 4. The remaining terms I can factor out a negative 3, and I'm left with x plus 4. And so my two factors are 2x minus 3 and x plus 4. And I take each one of those, set them equal to 0. 2x minus 3 equals 0. X plus 4 equals 0. And so x is equal to 3 halves, or 1.5, and x is equal to negative 4. And so these are our boundaries on our number line. So here's a picture of our number line. Our first interval created by our boundary points goes from negative infinity to negative 4. Our next interval goes between negative 4 and 3 halves, or 1.5. And the last one's from 1.5 to infinity. And we could go ahead and even make this a bracket here because I know this point's going to have to be included because of this symbol on my inequality, the little line. And so I'm going to go ahead and make these into brackets. Also in the middle, these would be brackets if that's where we shade. And so now I'm going to choose a point to test in each interval. This interval I might test -5. And remember, we do that by replacing the x's in our original inequality with a -5 to see if it works. In the center section, I might test 0 because that's always easy to test. Test 0. And in the last section, I'm going to test the number 2. And the next slide is going to show us those test values. Okay, so here's my test slide. I tested -5 in the first interval and found that that was true. Tested 0, found that to be false. And then in the last interval I tested 2 and found that to be true. And so therefore, I have to have the union of these two intervals, excluding the center section, and therefore I'm going from -∞ to -4 in union with 3/2 to 2. And notice that I did have to change a couple things on this slide, so if you printed them off the MyMathLab website, there were some errors on there. And so if I were going to graph this on a number line, I would have a number line similar to this. A number line in which each part was shaded that way, but not the center part. Okay, and the last type of inequalities we need to discuss are rational inequalities. Remember, a rational equation is where you might have a variable and a denominator of a fraction part. And so first it's necessary for us to rewrite the inequality so that the zero's on one side and there's only one fraction on the other side. Next step is to determine the values that will cause either the numerator or the denominator of the rational expression to equal 0. And these values give us our intervals on our number line. So step 2 is where we get our boundaries that we were doing similar to the inequalities, but we get them a slightly different way here with rational inequalities. And then just like the quadratic inequalities, we're going to test a value in each of the intervals. And we do have to be careful with the symbols on this, because just because it might be a less than or equal to symbol, the one with the line under it, does not necessarily mean that value is included, because we have to be careful of what would cause the denominator to equal 0. And so we'll be talking about that with the next couple of examples in the video. Okay, so this is just a word of caution. If this particular inequality were just an equation, then we could certainly multiply through by x plus 4. But we can't do that in an inequality situation, and so we need to be careful of not doing that and making that mistake. Okay, so here's my rational inequality. I know it's rational because the variable's in the denominator of a fraction. And so step 1 told me that I have to move everything to one side and make everything one fraction on one side. So my first step is to subtract the 1. And so I would have 5 over x plus 4 minus 1 is greater than or equal to 0. Now to make this into just one side with a fraction, I'm going to have to transform this -1 into something that has a common denominator with x plus 4, which of course I'm going to have an x plus 4 as my denominator. So this is going to become 5 over x plus 4 minus x plus 4 over x plus 4, which is greater than or equal to 0. And so now that I have a common denominator, I can combine my numerators. I'm going to have 5 minus x minus 4 over x plus 4. Now notice here that I subtracted both the x and the 4. That's a common error also when people are subtracting. Now I'm just going to simplify my numerator, and that's going to give me 1 minus x over x plus 4, which is greater than or equal to 0. And so from this point, I'm going to be into step 2, where I can determine my boundary points. And so I take the numerator, 1 minus x, set it equal to 0, take the denominator, x plus 4, set it equal to 0, and that's going to give me my 2 boundary points. So in this case, I'll have x equals a -1, and in this case x equals -4 for my two boundary points that create my intervals. Excuse me, this should be a +1 because we'd have to divide by the -1 with the x. So I have +1 and -4 for my two boundaries. So here we see a picture of each of the intervals created by the boundary points that we just found with our rational inequality. And now our job is to test a value in each of these intervals to determine which one is going to be included and which one is not. And you'll notice that the 1 is already colored in, but not the -4, even though the symbol is one with a line under it. And the reason being, I cannot include -4 because if I do, -4 plus 4, that would give me a 0 in my denominator, which the I cannot do. And so therefore only the 1 would be included as far as the boundary points go. And so I'm going to probably test a value of -5 here. That would be on this side. These are my test values. Of course, I'm going to test 0 in the center, and I'm going to test +2 in this boundary. And just like when we were testing our intervals with the quadratic inequalities, we're going to take each of these values one at a time and substitute it in here to see if it satisfies the inequality. And if it does, then that interval will be included. Okay, so this slide shows us these values tested. When I test the -5, I get a statement that's false, so that's intervals not included. When I test a value of 0, I get a true statement, so that value is included. And when I test a value of 2, I get a false statement, therefore that interval is not included. And so then it would be the center section of my number line, which would be this interval notation here, which happens to be another error that Pearson made. So from -4 to +1. And if I were going to graph this on a number line, it would appear as the center section shaded. And so I'll show you that now. So shaded from -4 to +1. Alright, this will be our final example. It is also a rational inequality. This one's slightly more involved because we're not just dealing with a 1 over here, so getting the common denominator takes a little bit more work. But just as we did with the previous example, we need to get everything to one side, so subtract the 5. And we're going to make this into one fraction. And since this denominator was 3x plus 4, then I'm going to make the 5 have a denominator of 3x plus 4. And I have to do 5 times 3x plus 4 in the numerator. And so that's what they've done in these steps. And so now we're going to distribute the -5 to the other two terms in those parentheses. And so once that's distributed, I get -15x minus 20. I'm just going to combine some like terms in the numerator, and I get -13x minus 21 over 3x plus 4. And so now I'm going to take the numerator and the denominator and set them equal to 0 so that I can determine my two boundary points for the intervals on my number line. So that's been done for us here. Solving for x, I get -21 over 13. Solving for x here, I get -4/3. And here we see the intervals broken apart by our boundary lines. And notice neither boundary point is shaded in because my symbol is not shaded. Does not include the equal to or part. So, therefore, I don't have to worry about which one is included because neither of them are included. And so now I'm going to choose a value in each interval to test. And so over here, I'm going to test a value of -2. In the middle, 0 is not included this time, so be careful, 0 is not always in the middle. So I'm going to have to choose another value, -1.5. 0 is in this interval though, and I'm going to choose it for the final test point. Okay, so testing those values into my original inequality, I find that the first interval, A, and the third interval, C, give me an inequality that is true. And therefore, since I don't include the middle interval, I have a union of those first and last intervals. And that will conclude the video for section 1.7. If you have any questions, please don't hesitate to email me, as well as with your My Math Lab assignments. I'll be happy to help you with those. And I will see you in class on Tuesday, the 4th.